In this video, we're going to look at the P series. Find the values of P for which the series summation n equals 1 to infinity 1 over n to the P is convergent. So our goal is to find the values of P for which this series converges. Now notice that if P is less than 0, then the limit as n goes to infinity of 1 over n to the P, which is equal to limit as n goes to infinity, n to the minus p, this limit will approach infinity. So we can say that the summation 1 over n to the p, n equals 1 to infinity, diverges by the divergence test. Recall by the divergence test, if the limit of the nth term as n goes to infinity is not 0, then the series diverges. And the limit as n goes to infinity is equal to infinity, which is not 0, so the series diverges by the divergence test. Now, let's consider the case if p is equal to 0. If p equal to 0, then the limit as n goes to infinity of 1 over n to the p is equal to limit as n goes to infinity of 1 over n to the 0, which is equal to 1. So it's a limit as n goes to infinity of 1 divided by 1, which is equal to 1. And therefore, summation n equals 1 to infinity 1 over n to the p diverges. It diverges by the divergence test because the limit of the nth term is not 0. The limit of the nth term is equal to 1. Diverges by the divergence test. Now let's consider the case p equals 1. So if we have p is equal to 1, that gives us summation 1 over n to the power of 1. N equals 1 to infinity. Let's just write this as summation 1 over n. N goes from 1 to infinity. And this is a divergent harmonic series that we proved in an earlier video to be divergent. So this is a divergent harmonic series. Now let's consider the case p larger than 0 and p not equal to 1. So we have summation 1 over n to the p. N goes from 1 to infinity. And the corresponding function will be f of x is equal to 1 divided by x to the p, which is clearly positive, so it's positive valued. F of x, the y values are positive for all x values. So the y values are positive. I should say it's positive for x larger or equal to 1. It is continuous for sure, and also decreasing. Why is it decreasing? It's because the denominator is growing larger while the numerator is just a constant, so the ratio decreases as x increases. So the integral, so now we can apply the integral test. Integral from 1 to infinity 1 over x to the p dx is equal to integral from 1 to infinity x to the minus p dx. Reversing the power rule, we get x to the negative p plus 1 divided by negative p plus 1, evaluated from 1 to infinity. So this is equal to 1 divided by 1 minus p. It's an improper integral, so we take the limit as x goes to infinity of x to the power of 1 minus p, minus, and plug 1 in. We're applying fundamental theorem of calculus, so we just get 1 to the power of minus p plus 1. That's just 1. Now, notice that the limit as x approaches infinity of x to the 1 minus p will be equal to 0 if the exponent is negative. If the exponent 1 minus p is negative, or equivalently, when p is greater than 1. So notice, if you have infinity to the power of -1, that's going to go to 0. You get 1 over infinity, and that's going to be equal to 0. So when the exponent is negative, x to the 1 minus p will be 0. All right, so we can tell that for p larger than 1, the integral from 1 to infinity, 1 over x to the p dx, is equal to 1 divided by 1 minus p times the limit as x goes to infinity of x to the 1 minus p minus 1. And we proved that when p is greater than 1, the limit as x goes to infinity of x to the 1 minus p will be equal to 0. So the result will be 1 divided by 1 minus p times 0 minus 1. So the integral, 1 over x to the p dx, integrated from 1 to infinity, these are the limits, is equal to 1 over p minus 1. So it converges. The improper integral converges for p greater than 1. We now found the values of p for which this p integral, this p series, basically converges. Now let's apply the integral test. Since the integral from 1 to infinity, 1 divided by x to the p dx, converges for p greater than 1, the corresponding series, the series, which is known as a p series, the series summation n equals 1 to infinity, 1 divided by n to the p, converges for p greater than 1 by the integral test. We must always state that, by the integral test. Now let's consider p less than 1, larger than 0. That means the integral from 1 to infinity, 1 over x to the p dx. If we integrate this, we're going to get 1 over 1 minus p, the same antiderivative we had before. Limit as x goes to infinity of x to the 1 minus p minus 1. But now notice that the limit as x goes to infinity of x to the 1 minus p will be equal to infinity, because this exponent is now positive. If p is between 0 and 1, 1 minus p will be a positive exponent. So you have something like, for example, infinity to the 1/2, which is going to go to infinity. So for that reason, the integral from 1 to infinity, 1 over x to the p dx, diverges, and by the integral test, the corresponding series also diverges. By the integral test, the series summation n equals 1 to infinity, 1 over n to the p, also diverges. Diverges for p less than 1, larger than 0. Let's do a summary. So here's the summary. The p series summation n equals 1 to infinity, 1 divided by n to the p, is convergent if p is greater than 1, divergent if p is less than or equal to 1. Let's look at some examples. Summation n equals 1 to infinity, 1 divided by n to the 3/2. This is convergent because it's a p series with p equals 3/2, which is greater than 1. If p is larger than 1, the series converges. Summation 1 over root n. Here, we can see that p is equal to 1/2 because we can rewrite this as summation 1 divided by n to the 1/2, n equals 1 to infinity, and the value of p is equal to 1/2, is less than 1. For this reason, this series is divergent because it's a p series with p equals 1/2, and 1/2 is less than 1. All right, let's look at some examples. So here we have part A, question A, summation n equals 1 to infinity, 1 over n to the 1.1 plus 1 over n to the power of 0.9. Let's split up the sums, so we can write this as summation n equals 1 to infinity, 1 divided by n to the 1.1 plus 1 divided by n to the 0.9. This is equal to summation n equals 1 to infinity 1 divided by n to the 1.1 plus summation 1 divided by n to the 0.9. Now we can evaluate the series, the sum separately, because we have the sum of two separate series. Now, the first series is a p-series. In fact, they're both p-series, but one of them will converge and another one will diverge. Summation, the first series on the left, summation 1 over n to the 1.1, n equals 1 to infinity, is a convergent p-series. Why is it convergent? Because p is equal to 1.1 greater than 1. Convergent p-series with p is equal to 1.1 larger than 1. However, the second series, summation n equals 1 to infinity 1 divided by n to the 0.9, is a divergent p-series. Divergent p-series with p is equal to 0.9 less than 1. That means the entire series is going to diverge, because if one of them diverges, the whole thing diverges. So summation n equals 1 to infinity 1 divided by n to the 1.1 plus 1 divided by n to the 0.9, the entire series diverges. Alright, so the key concept is the reason that the whole series diverges is because summation n equals 1 to infinity 1 divided by n to the 0.9 diverges. It diverges because the value of the p is equal to 0.9 less than 1. For this reason, the entire series will diverge. N equals 1 to infinity 1 divided by n to the 1.1 plus 1 divided by n to the 0.9, this entire series will diverge. Alright, part B. Here we have summation n equals 1 to infinity 1 divided by n plus 3. We can't apply the p-series directly. Why is that? The reason is because we don't have the pattern of a p-series. The p-series pattern is 1 divided by n to the p. Here we have 1 divided by n plus 3. So we can't apply the p-series directly. But what we can do is we can rewrite this. Let's rewrite n equals 1 to infinity 1 divided by n plus 3. We're going to rewrite this as we're going to subtract 3 from n plus 3 and add 3 to the index to compensate. So we get n equals 4 to infinity 1 over n. These two are equivalent. If you plug n equals 1 in the expression on the left, you get 1 divided by 1 plus 3, 1 over 4 as the first term. If you put n equals 4 in the expression 1 over n, you get 1 over 4 as the first term. If they start at the same place, they will all the other terms will be equivalent. So both of these series, both series are equivalent. And we made them equivalent because we subtract 3, from n plus 3, and we added 3 to the index n equals 1 to compensate to the index n equals 1. So now summation n equals 4 to infinity 1 over n is a divergent p-series. Divergent p-series with p is equal to 1. Now it follows that summation n equals 1 to infinity 1 divided by n plus 3 also diverges, because this series is equivalent to the p-series that diverged. 1 over n plus 3, this is equal to summation n equals 4 to infinity 1 over n is equal to 1 over 4, let's expand it, 1 over 5 as a second term, 1 over 6, 1 over 7, and so on. So this is a divergent p-series with p equals 1 without the first three terms. But we know that adding or subtracting a finite number of terms does not affect the convergence or divergence of a series. All right, thanks.